Swayam Prabha. Digital India. Educated India.
Going to solve a numerical example just to explain the working principle of this particular the n piece. Now, here I am just going to take one example, numerical example for a system. It is a very simple system having 2 inputs and 1 output. So, this is something like this. We have got I1, I2 and I have got only one output. Now, the statement of this particular the numerical example is as follows. So, we will have to model, we will have to design one n phase, and the purpose is to model a process having 2 inputs I1 and I2 and one output, that is O. Now, in this particular n phase there are 6 layers and we use 2 linguistic terms to represent each of the input parameters for simplicity. For example, say to represent I1, so we have used like your low and your high. Similarly, to represent this I2, the second input parameters, so we have used 2 linguistic terms, one is called the small, another is your the large. So, this is a very simple the n piece, and the 2 inputs, each of the 2 inputs is represented using 2 linguistic terms. So, we have got like 2 multiplied by 2, so only 4 possible rules, and we can see that. So, this shows actually the second layer. Now, in the second layer, in fact, we have got 2 neurons here and you have got 2 more neurons here, and the connecting weights between your the first layer and this particular neuron of the second layer. So, this is nothing but is your V11, this is your V12, and here the connecting weight is V23 and this is your V24, and it is a very simple network. Now, let us see the other part of the statement of this particular problem. The connecting weights are lying in the range of 0 to 1, and if you see the membership function distribution which you have considered for the 2 inputs like I1 and I2 are as follows. Now, for simplicity we have considered like the low I1 is nothing but this. So, this type of membership function distribution, right angle triangle, and for the high another right angle triangle, and there is overlapping also. Now, similarly for this I2 there are 2 linguistic terms, one is the small, another is the large, and for simplicity we have considered. So, this type of your right angle triangle. It is a very simple representation of the membership function, and here the starting value of this particular I1 and I2. Now, you can see that the starting value is nothing but I1 minimum and here it is I2 minimum. So, this I1 minimum we have considered that is equals to 1.0, and your I2 minimum we have considered that this is equals to your the 5.0. Now, the rest of the statement of this particular problem, like we use the connecting weights like V11 is equals to V12, and that is denoted by is your the D1. Similarly, your so this particular V23 is nothing but is your V24, and that is going to represent actually your D2. Now, these values for the D1 and D2 should lie in a particular the range, and there should be some well defined range also. And as I told, there are 4 possible rules, 2 multiplied by 2, and the output of a particular rule, that is the output of the ith rule, that is y I, is nothing but a I 1 plus b I 2 plus c I, and here, so this particular I is nothing but 1, 2, 3, 4 and A I, B I, C I are the coefficients of these particular the rules. Now, here to solve this numerical example, so we are going to consider some numerical values, the predetermined numerical values for this particular the coefficient. The values of the coefficients are as follows. Now, for the first rule, the coefficient, the values of the coefficients are nothing but A I, that is A 1 equals to 0.2, B 1 equals to 0.3 and C 1 is 0.10. Similarly, for the second rule, A 2 is 0.2 and this B 2 is 0.4 and C 2 is 0.11. Similarly, for the third rule, your A 3 is 0.3, B 3 is 0.3 and C 3 is 0.13, and for the fourth rule, your A 4 is 0.3, then B 4 is 0.4 and C 4 is 0.14. Now, this D 1 and D 2, so they are varying in this particular range. So, D 1 is varying in the range of 0.8 to 1.5. Now, similarly, D 2 is going to vary in the range of 4.0 to 6.0. And to carry out this numerical example, actually what we do is we assume the values for the connecting weights. We assume that V 11 equals to V 12, which is going to represent the membership function distribution for the first input, that is nothing but 0.3. Similarly, V 23 equals to V 24, this is nothing but 0.5 and these are in the normalized scale. So, we will be discussing that using these normalized values. So, we will have to find out the real values lying in the range for this particular D 1 and D 2. And we are going to determine what is the deviation in prediction for a particular training scenario, where I 1 the first input is nothing but 1.0 and I 2 that is the second input is 6.0 and the output O is nothing but is your 2.3. Now, let us see how to determine the output corresponding to, so these set of inputs, and how to determine the deviation in prediction corresponding to this particular the training scenario. So, those things actually I am just going to calculate. Now, let us concentrate on the solution of this numerical example. Now, as I told, the first thing we will have to do is corresponding to the normalized values of the connecting weights. So, we will have to find out the real values, that means we will have to find out the real values for this particular D 1 and D 2. Now, to find out the real values from the normalized value, that is denoted by n, we are going to use this particular the formula. It is very simple, like x is equals to n multiplied by x max minus x minimum plus x minimum. Now, if I put n equals to 0, so if I put n is equals to 0, so x will become equals to how much? That is nothing but x minimum. On the other hand, if I put n is equals to 1, what will happen to the value of x? So, if I put n equals to 1, so this is x max minus x minimum plus x minimum. So, this will become your x maximum. That means, so here, so this particular n varies in the range of 0 to 1, and accordingly I can find out what should be the real values for D 1 and D 2 lying within their respective ranges. Now, here, so D 1 is nothing but your 0.3 multiplied by 1.5 minus 0.8 plus 0.8, because n is equals to 0.3, the maximum value of D is 1.5, the minimum value is 0.8, and if we calculate, we will be getting that D 1 is equals to 1.01. Now, similarly, we can find out D 2 is equals to 0.5, that is the value of n, multiplied by 6.0 minus 4.0 plus 4.0. Now, here the D2 minimum is 4.0, D2 maximum is 6.0 and value of small n is equals to 0.5, and if you substitute you will be getting the value for this D2 as 5.0. Now, once you have got the real values for this particular D1 and D2, so now we are in a position to draw the modified membership function distribution for this particular I1 and I2. So, for this particular I1, so this is the modified membership function distribution, and for this I2, so this is the modified membership function distribution, where D1 is nothing but this and D2 is nothing but is your this. So, we can find out the modified membership function distribution for the two inputs. And now, the layer wise I am just going to carry out the calculations. Now, on the first layer, as I mentioned that we use linear transfer function. So, this output is nothing but the input. So, the output of the first neuron lying on the first layer is nothing but the input of the first neuron lying on the first layer, and that is nothing but 1.1. Now, similarly, the output of the second neuron lying on the first layer is same as the input of the second neuron lying on the first layer, and that is nothing but 6.0. Now, layer 2 is nothing but the fuzzification layer. So, what you do is, so these values for your the input, that is 1.1 and 6.0, we are going to pass to the corresponding the membership function distribution just to calculate what should be the membership function values. Now, if you calculate the membership function values, so you will be getting that your corresponding to the low I1. So, the mu low corresponding to I1 star. So, this will become equal to your 0.900990. Then corresponding to your I1 star, the mu h will become 0.09009. Similarly, corresponding to the second input, that is equals to 6.0. So, we can find out the mu values like mu sm corresponding to I2 star is nothing but 0.8. Then comes your mu large corresponding to I2 star is nothing but is your 0.2. And how to determine those things we have discussed several times in details. Now, then comes your layer 3. Now, this layer 3 is actually is going to represent all the 4 possible rules for this particular the reasoning tool, and here you can see that the input of the first neuron lying on the third layer is nothing but the 2 values of the membership. Similarly, the input of the second neuron lying on the third layer are nothing but the 2 values of the membership. Then your the input of third neuron lying on the third layer is nothing but this. Then the input of the fourth neuron lying on third layer is nothing but this. And what you will have to do is, now to determine the output of third layer, so we will have to multiply your the mu values. For example, say output of the first neuron lying on the third layer is nothing but mu low corresponding to I1 star multiplied by your mu sm corresponding to this I2 star. And if you substitute the numerical values and multiply, so you will be getting W1 as actually your the firing strength for the first fired rule. Now, by following the same procedure, so we can find out the firing strength of the other fired rules. For example, for the second rule, the firing strength we can find out, and this will become 0.180198 as W2, and similarly we can find out the firing strength of the third rule, that is your W3, and that is nothing but is your 0.07 9207. For the fourth rule, so we can also find out the firing strength, and that is nothing but mu h corresponding to I1 star multiplied by mu LR corresponding to I2 star, and if you substitute the numerical values and carry out the multiplication, so you will be getting W4 is nothing but 0.019802. And once you have determined all the firing strength values, now we can start with layer 4, and in layer 4 actually we try to find out the normalized values of this particular the firing strength. Now here, so W1 bar, that is the normalized value for the first the fired rule, that is nothing but W1 divided by W1 plus W2 plus W3 plus W4, and if you substitute all the numerical values, so you will be getting W1 bar as 0.720792. Similarly, this W2 bar is nothing but is your W2 divided by the sum of all W values, and if you substitute the numerical values, you will be getting W2 bar is nothing but 0.180198. Now, by following the same procedure, so we can also find out like what should be your W3 bar, and W3 bar is nothing but W3 divided by the sum of all the W values, and you will be getting 0.079207 as your W3 bar. Similarly, W4 bar is nothing but W4 divided by the sum of all W values, and after substituting the numerical values, we can calculate the W4 bar is nothing but 0.019802. Now, we have got all the normalized firing strength values. Now, we go to layer 5. Now, in layer 5 actually what you will have to do is, so we will have to find out the output of each of these particular the fired rule. For example, for the first fired rule, so this W1 is nothing but A1 I1 star plus B1 I2 star plus C1. So, you will be getting 2.12. Similarly, this Y2 is nothing but A2 I1 star plus B2 I2 star plus C2, and this will become equal to 2.73. Then Y3 is nothing but A3 I1 star plus B3 I2 star plus C3, and if you substitute the numerical values, you will be getting 2.26. Then Y4 is nothing but A4 I1 star plus B4 I2 star plus C4. So, if you substitute all the numerical values, you will be getting 2.87 as your Y4. Now, once you have completed your the layer 5, so layer 5 actually we will be getting, we multiply. So, this W1 bar by your Y1, and we will be getting this as the output of the first neuron lying on the fifth layer. Similarly, the output of the second neuron lying on the fifth layer is nothing but W2 bar multiplied by Y2, and you will be getting 0.491941. Similarly, the output of the third neuron lying on the fifth layer is nothing but W3 bar multiplied by Y3, and that is nothing but 0.179008. And similarly, your the output of the fourth neuron lying on the fifth layer is nothing but W4 bar Y4, and if you substitute the numerical values, you will be getting 0.056832. And once you have got the outputs of the fifth layer, now in sixth layer actually what we do is we sum them up just to find out what is the overall output, that is your 601. So, 601 is nothing but W1 bar Y1 plus W2 bar Y2 plus W3 bar Y3 plus W4 bar Y4, and if you substitute the numerical values, you will be getting 2.255860, and this is nothing but the final calculated output for the set of inputs. Now, this calculated output will be compared with this particular target output, and that is denoted by TO1, that is 2.3, and very easily we can find out the deviation in prediction, and we can also find out the mod value of the deviation in prediction, that is 2.3 minus 2.55860. Now, here fortunately we are getting positive, but if we get negative, so we will have to consider the mod value, and the way I discussed. So, this is the prediction corresponding to your the first training scenario, then we go for the second training scenario, third training scenario, up to all the training scenario. So, capital Lth training scenario, and try to find out all the deviation values. You add the mod values of all the deviations, find out the average, that particular average will be the fitness of the GA as I discussed. Now, if I use the GA string and if I use a binary coded GA, say if I use a binary coded GA, for each of the GA string I will be able to find out the fitness, and then we use actually the operators, the GA operators just to modify, and GA through a large number of iterations we try to evolve that particular NPs, like which will ensure a very good prediction accuracy. Now, this is the way actually this NPs works, and now regarding the reference, you can see the textbook for this particular course, that is Soft Computing Fundamentals and Applications. If you want to get more details regarding this, the Neuro-Fuzzy systems. Now, to conclude, actually in this lecture we discussed two Neuro-Fuzzy systems. The first one is based on the Mamdani approach, and the second one is based on the Takagi and Sugaina's approach. Now, the basic the aim of this particular the Neuro-Fuzzy system is to design and develop the fuzzy reasoning tool, and we take the structure of this particular network so that we can represent the fuzzy reasoning tool, and we can carry out the training or the optimization of this particular network. But truly speaking, we are going to design and develop very accurate fuzzy reasoning tool, and we have discussed both Mamdani approach and Takagi and Sugaina's approach of fuzzy reasoning tool, and we have seen how to represent them using the structure of a network and how to optimize. So, how to evolve the optimal fuzzy reasoning tool based on both Mamdani approach as well as Takagi and Sugaina's approach by taking the help of the structure of a network, neural network, and with the help of one optimization tool. Now, so this is the way actually we can develop the Neuro-Fuzzy systems, and these Neuro-Fuzzy systems have got a large number of practical applications. So, these Neuro-Fuzzy systems have been used widely to solve a variety of real world problems. Thank you.